Load. Oh my gosh. Feels so important, right? So we will have deflection control, right? Because we don't want it to crash. Okay. So this is a column, as you know. So you start it.
We can start any moment. Right?
Yeah.
What's the rate? 1 millimeter per minute.
1 millimeter per minute. You heard it. Yeah.
Okay. So just like the last time, when you see the force here increasing. So at the beginning, it's just noise. There is a little bit of play between the ball and the pin. So let it lower down a bit before there is seeing some of those happening. I don't know how it's going to react. So it's already a kilonewton. So the calculated value was at 10 kilonewtons. As I said in the previous test we ran, we added about 13. Let's see, we'll reach a maximum load. Critical load and then start dropping again as it flattens out. We are at 10 kilonewtons now. And it's dropping. I think is it? Yeah. So it started to drop again. So I think the peak was at 11 and the estimate was at 10 and above. So the value was increasing 10.53.
Yeah, you see it from the side.
Is buckling.
So once one is up here, you decide where to stop it.
We've gone 3 millimeters now.
3 millimeters. Are you measuring lateral deflection also?
No, not this way. I don't think you'll see much there.
Okay, we can do one thing. Assuming it's an elastic, okay, we can download, unload it and see if it gets straight back again.
Yeah.
Okay,
Well,
can you do it?
This,
You go,
but if
no,
we move it vertically, the bolts will pull it.
pull. We just want to go to the original position.
I think what would make sense to take the load to zero.
Load 0.
Yeah. So we'll rise it so the load gets to zero. Then we'll do it like that.
If it is within elastic limit, that is that elastic equation is, right? Yeah. So it should be getting straight, right? Let's see whether that happens or not.
Yeah, stop. Slightly up fast so that this comes down.
Yeah. I think it has almost got straightened, right? Yeah. So there could be residual stress all the time, depending on how you.
Now there is no load applied. So that curvature you have is a permanent deformation.
Yeah, it looks straight, eh? It's almost
But there is
straight.
a little bit of a deflection.
It could be happening because of some residual strain on the surface that might have yielded it.
So you have a slight
Little bit, yeah. Slight bend is there. Okay. But the failure happened the moment it started lateral deflection. Okay.
So we can take that out
Okay.
and they can see the slight.
Yeah. Send it to take it off and give it to them.
That's what is just finishing up.
Next time, Armando, we may put some lateral deflection, the peak load and lateral deflection. Now we can see that whether they coincide. Eh?
Yeah,
Yeah.
absolutely, yeah.
If they want to have a
Try the shorter column at the same load, or you want to just do this one?
no, you can do the shorter column.
We can
just
take
crash
it to
it.
the same load to show, yeah.
You want to have a look at it?
And you can see
This one, 15 inches,
15 inches. And that one was
34.
34.5.
so this is a column with the same cross section, but the length is that was 34. This one is 15. Okay. So which one will take more load? Short one, right? We have to see whether it has got compressive failure or it fails by lateral buckling. Okay.
Yeah, I couldn't reach. I'm trying.
Yeah, it's only it's a small bit.
This is like
Armando,
Yep,
we have to do some testing.
it's getting all recorded.
Do you record? Okay.
That's okay, so you know it's getting all recorded.
No, we'll drop it later. We switch it off. I think I know the time. Okay, guys, the load has started, right? No, it's going to start shortly.
Okay, when you go, I go maybe half millimeter. It was pretty quick. Let's try half millimeter. Otherwise, it's okay. If you're already set with fuel, it's okay. Just leave it. It's okay. So the test has started. Okay, there we go.
What I can try to do is reset the interlock from this here.
Yeah. Okay. So first review, see what happens.
That's going.
Okay, guys, so it's started. Yeah.
So we'll reach a similar load and then we'll stop the test. We're not going to take it to critical because it will be too high.
So it is carrying more load. Okay.
Yeah.
So we'll say that we are not going to doing the
Show them
compression.
at the same value, it will just
You just seal
stop.
straight.
Yeah. We can go
Or maybe
higher.
10% higher. Okay.
Yeah, for sure. Yeah, I can go like 12,
How much was the
13.
11? 12, 13. Yeah. Stop at 13. Okay. So that will be 20% higher. Okay. So, guys, what is going to happen, that short column, because it can take a lot of load. Okay. We will go excess of that 11 what we had last time, maybe 13. Then we'll stop it, showing that it is already has got higher load than the longer column. Okay.
So yeah, we don't want to go too high because of the bearing load that was mentioned. There, load is already loading on the holes. So if we go much higher, we may have a failure at the end of the beam and then we back it. Stop it. Yeah, it's not going to explode. It's not great. It's going to collapse. But
You like to see some explosion, right?
yeah, that's what he was asking. What were the expectations when he came in?
Yeah, I'm at 12. Stopping.
Mr. The load is already 12. Okay. Maybe you put to 13. That's the stop it. Okay. So it's reaching 13 now. Yeah, stop it.
It's curving, right? Even if it's not buckling, what do you think is happening? So this is acting like a spring that you're compressed, right? So you expect to see a linear response, but it's going up and now it's starting to changing the curve is not linear anymore, but it's not buckling. So what does that mean?
What is it happening? If it is not buckling,
So if you look at the curve, what's going linear and then it's starting to curve. When you have non-linear response, something is happening that is not elastic anymore.
before that something happens. Plastic, so it's
But
yielding.
what is going on? Yeah, it's plastic. But what is plastic? Obviously, this section is easily holding that load. It's not buckling. The holes the holes, what I've been saying, the bearing load is too high. They're ovalizing, they're stretching out, right? So that's why you're seeing the thing keeps on moving, the machine keeps on moving, but the holes are stretching out.
Okay? Okay, fine, thank you very much. Now let's go to the beam.
You see the holes are ovalized.
So, 34
Yeah,
inches.
yeah, yes.
You know those? You know the dimensions?
No, I don't know.
You should know the dimensions.
The 34 inches, yeah.
Good. So the 2 points at the bottom here are spaced with 34 inches. And up here, they are about 12 and a half inches. It's a different setup as 352. Okay? And it's centered, so you have to do the math. Right? And this section is 1 inch by a quarter.
We'll provide you all the dimensions, okay?
Yeah.
Well, yeah, you definitely want to run this fast. So for buckling, we had shims placed at these two sides, so that when we push down, it will stay, this piece will stay flat. Now we remove them, and it's allowed to oscillate, because you want to make sure that the load of each of the fingers. We can do 3 because that's going to move pretty, yeah, quite a bit. So if we're running all those tests. So we'll be moving at 3 millimeters a minute instead of being only 1 millimeter. There will be a lot more deflection happening here. So we're moving faster.
I don't see the setup for.
What is it?
Oh, I lost my. Okay.
That's not here. Okay, so instead of running the test, That is where, when you have instruments, you have to size the instruments for what you test. So if you wanted to be precise about this, and you know that the load is at about, what is it, like 50 newtons, 60 newtons. So this machine is weighted. And then even the load cell is measuring this is very much right. This will go up to 250 newtons. So you want to have a load cell and maybe only measures maybe 400 newtons. So that the resolution matches the level of space. You're doing, then you wouldn't have such a big wiggly plot. This would be a lot more precise results. Yeah, we have a range of those cells. And all of you can measure exactly for that. You're measuring something that doesn't break at such a high load, you want a bunch of those cells. Just like you use a measuring tape for something coarse.
What time is the next one?
1:15, so we are a little 10 minutes left. Okay. So they will come probably, run it quickly so that we can finish it.
We can run it faster for the rest,
Yeah.
right?
Yeah, the others you can run them. But this one I figured I was going to flat very slowly, so.
We deflected 10 mil.
So this is like the usual time lapse. You see the time lapse, and this is the very close.
The problem is the speed you're loading at will increase the force, right? If you go faster, you just kind of fix the rest of that tiny bit. No? I'm assuming.
It will affect a little bit.
It will affect a lot, but not that much. Every loading rate has got an
Wood will crack reinforced, right?
but wood does not take much load either. So
4 newtons or something. That was the steel. 4 or 5 steel pipe.
so get the steel pipe close by as soon as it goes. This one, how far you want to go?
I don't know, it's up to you.
Is it yielding? Is it showing the yielding? No.
We are like,
This is the deflection, right?
Yeah.
It has not flattened yet.
no, it's gonna keep going.
No, at one point it will be flat.
It's gonna take a while.
It should, at one point it should.
You might be starting now.
It's starting now maybe.
Or it's ramping up now and it's gonna,
Which one is the load?
it's going backwards.
Displacement.
It's going this way.
So load isn't doing that way. So it will go like this.
It's loading still.
The still load is increasing.
Then you deflect the 20.
Will be short of time.
It's okay, I can load the other one at 5 millimeter per minute. In
Yep.
the,
But then you have to do the timber, right?
there's a steel pipe still.
No, steel pipe, then timber.
Yeah.
Two timbers.
Yeah, 2 square ones.
So
and
next,
I-beam, you want to
yeah.
we can do all of them. They're gonna wait.
Well, they will wait, but I have to leave 10 to 2. Okay,
That's
you
okay,
can do
we
it.
don't need to.
Yeah. And if somebody wants to leave early, you say that video recording will be there. Watch that. Okay. It's taking a little bit of time. In the hindsight, we might have increased the loading rate or displacement rate. Okay. Do you have any class just after this? No.
I do. I have law, engineering law, but that's because I'm in. That's a
No. You can leave because the recording will be there. Okay. We'll post the recording. Okay.
No, that's until after. I think we're done. Yeah, it's supposed to end at 1:15 because there's a yeah, our class is scheduled at 1:50, so I'm fine.
But this one may continue a little bit more, and they will probably wait a bit. Okay.
The other people have gone.
Maybe what is happening now? It may be sliding, but it should not carry extra load for that. Okay.
I don't
Load
know
is still
what
increasing.
did you do last year?
I don't remember it. Yep, it's coming.
That's it.
That's it. It's coming. Yeah, you can see it's getting flattened, right?
It's still elastic.
Still elastic, huh?
No, too much is goes. Oh, it's deposit. Oh,
It looks, maybe the slope is reducing now, no?
where it's reducing. No, it's not.
Keep on increasing again.
It should be same.
No, it's increasing.
Wow, this beam can take so much load.
Yeah, we should have loaded it at a much higher
Yeah,
speed.
maybe like
Next time.
5 millimeter per second.
Yeah.
I can help. Big time ahead.
Let's keep on increasing.
long column，然后一个是 short column，这个是 beam。把凯麦啊，因为凯边当够嘛，竖着样，或者是竖着样。哦对，还有水泥还是钢，然后就出现buckling。
No.
Long column would be buckling first before yielding, and short column 是先yield。yield 是你在这个。因为他说这个比较，因为他弄得特别慢。 每次弄这个漏的弄的就是慢，刚刚最开始的时候0.2，现在才0.4磅，就是压力变形，这个是压的。
How much load it can take? Just let it do it.
Yeah, this one. I've never run this one. We're gonna end up hitting the brackets below here.
Yeah. Let's see. But it's still carrying extra load.
We're half, not even half. It's deflected. I think it might be sliding.
Yeah, I was wondering if
But if it's sliding also, we're still carrying the load, right? Load is increasing.
Well, it's
It will
still probably
slide.
linear,
It will slide.
so-
It is still linear. But remember, we have loaded it into 2 points. Okay, so this distance is low, so moment is created is lower. If you put it at the center, probably it have done it by this time. Because moment at the middle is constant, right?
They,
No, they're all here. Next batch has not come back yet.
are they coming?
They'll be coming. They should be here at any time. You can change the rating now, right?
The speed?
Speed.
No.
The hollow section will have even extra more load, right?
You can go faster on
Yeah,
the,
6-7 millimeter. Otherwise, it will take too long. It's going. Every time I think it's starting, then it keeps on increasing.
Yeah, I think it might be sliding and then picking back up. Right? But it did curve a bit here. You can see it.
Let's see. Can you plot the full graph how it looks like? No, it starts from here, starts zero deflection. You cannot change it, right? It might have yielded, but we don't see the full curve, right?
I'm trying to remember what the failure in columns for long beams are, but I just can't remember it offhand.
Failure for the
Long beams, like we got
long
columns.
long column.
Short column, we got the
Buckling. Local buckling like a pure compression, right? And for the long, it's lateral buckling.
lateral buckling. Oh, okay.
Yeah.
Awesome. Thank you.
Where that you saw that, it's
Yeah,
bent.
I noticed it, but I just couldn't remember what it was called. Thank you.
No problem. I think, it may be, if you can see the full, is it the full graph?
No. But you get all the points.
Very soon it will touch. I think if we can see the full graph, it is difficult because it may be strain hardening, that effect is going on.
I have to probably stop and just before it touches there. Normally the beam should be in between the studs. I didn't pay attention there. We could have gone further.
Gone?
Yeah, it's not here. Okay, I'm going to stop it now.
Until you see the full curve. Okay, it's touching the bottom. So we stopped it there. We'll see how the results come. Okay? You can unload it now. Next time you put it at maybe 10 millimeter per second. Okay? Do it quickly. Otherwise it will go on for long. What happened to the next batch? Just a query. If you have got 2-point load, right? If you had the same at the center, instead of 2-point load, you had 1-point load. This is 1/3 point loading, I think so. Okay, and if it is the middle, will the load capacity will be higher, load carrying capacity, or lower? Lower. Okay. What will happen to the moment of resistance of the cross section? No idea? Huh? It will decrease? Moment of resistance of the cross section. If you change the loading position, will it change or not? There are two answers. It will change or not change, yes or no. Okay? Yes, it will change. No, it will not change. Okay. If I say the correct answer is no, how many of you will support it? What's the reason for supporting this one? Because I said so? Yes? That's the reason? Huh?
I don't think any of the properties in the moment resistance equation will change.
Yeah, that's true. If you look at the moment of resistance, it's a cross-section property, right? The moment is applied through this load. Okay? So load position may change, it may create different moment of resistance, but the cross-section property does not change. The beam's load carrying capacity is changing, but not the cross-section property. Right? Don't write it because my supervisor said it's right. Okay? Okay, I'll let me. Guys, we are getting little over time, so is it okay to wait here?
Yeah.
And someone, do you have a class just after it? No? So please be patient. I'm sorry, because first time you are doing, you didn't adjust the load rating. Okay? Another batch is coming. We have a couple of more.
But we don't got enough time.
We will be taking extra time. Okay?
Are we able to apply more load?
Huh?
Are we able to apply more load on it?
More load on
Yeah.
which one?
We won't be quicker.
Yeah, we should be taking more load. Okay? But this time you make sure the loading rate is 10. Okay?
Or do you want 6?
10.
10?
10.
10 per minute?
Yep.
Okay.
Let's see it.
Armando, 10 per minute, it says?
Yeah, let's run it a little faster because this was pretty slow. Yeah. He's not gonna bend as far,
No.
but may as well go.
But the load carrying capacity will be higher. You see.
Yeah. So maybe we'll go 5.
No,
same.
10, 10, 10.
Oh, 10, okay.
Let's see what
I have
happens.
to very be careful there, okay?
Huh?
I have to be careful when I do that.
Or do 8 then.
We'll test it. We'll go way faster. So same rules as time. There will be 10 minutes. Okay. The last test was 10 minutes.
So this cross section has got the same amount of steel, roughly, okay, to this plate section. So this load carrying capacity is expected to be higher or lower? Higher, right. It's yielding now? What is the load? Oh, it's the initial one.
We are 2 kilonewtons and 10 mil. It's starting to,
Last one was how much was the load?
I forget. I had to be careful with this,
Why?
so you don't touch the bracket, so I couldn't.
No, I'm keeping an eye on it. It's far away from the bracket. What was the load in the last case? Do you remember?
I think maybe we may gone down to 0.4, so about 400 newtons. I
400.
think. Somewhere around there.
How much is this one? 300
Right
now?
now it's at 3,000. Right now it's already at 3,000 newtons. So
And
it's
last
way
one?
up. I was maybe 400 or 500 newtons. So yeah, we can look it out. I think we're somewhere around there.
So it's definitely going towards yielding, right? Definitely this is
Well, they were not reaching.
reaching to the yield limit, right?
So it's a different way of holding it.
Yeah, I don't know.
There is more people in the back.
The second batch.
Oh, okay.
They have arrived at 115, but we didn't finish it.
Yeah.
So we told them to wait
Okay.
once we finish it, and they are okay if we go over time. Okay?
Okay.
They don't have a class immediately.
Yeah.
Okay. What was the I think last time we went to 34. You don't remember it.
It's getting there.
So this one not only can carry extra load, it is also much stiffer. That's why you don't see that deflection, right? You will get these questions in your assignment, so you can make critical comments. Okay. Another question which will be there also, I'll ask you to which one is more ductile. Okay, so you have to do a little bit of studying on that one, that how to define ductility. Okay, there are various ways to do that. I think I described in the class a little bit, but you can do your own studies. And I don't want everyone writing the same thing, so you can do a little study and see that how you can define ductility. Okay.
They can be following on their phone outside.
Hmm?
The group, your next group, they can follow some of the testing that we're doing at the end, and we just showed them the beginning.
First day you do it complete. They can wait. I think you can stop it. It's already in that range. Stop it. Yeah. I think we went up to the same, roughly around the same deflection. It's almost touching, right? So we'll stop it here. Then when you get the data, we'll send you the data, so you can analyze them and tell us, what is the it has definitely yielded, right? You're still applying load? Is it going inside? Yeah, it has reached to the peak. Now you can see it's going down. Or stop it. Okay. Okay. Now you are going to put the timber, right? Oh. Timber you do that 5 millimeter. Okay. Last time you did this one was too slow. Okay. We can take it off, right?
Yeah, it's good.
And show it to the show. Oh. It's not, it has not stopped yet. You can stop the test now.
Yeah,
So next one is the same thing. We are doing it for the timber, right? This is a almost like a square cross section, okay?
okay. Yeah.
You may see some explosion here now. Yeah, that's fine. This will not take much load, so it will crack quickly. The steel beam, you can almost idealize it. Each one will probably fail in the same way. But for the timber, it depends on the fiber orientations, right?
I got it before you did that. So it's good. Got two photos. I think I'll try to stop. It's like last.
It's failing. It's already gone probably.
Bring me the wet, the same as this.
It probably cracked. Then it started building again. This is the moist one. In timber, what may happen that some low moment areas, not the maximum one, you may see some fibers or some crack. Okay, that's why you may in between you can see some little change on stiffness, but it is still keep on increasing it, but eventually it will fail.
SPF number 2.
That's
What do
people.
you have for rings? Fine.
The line is here, you're over there.
Maybe for the next groups we can do for all the blending. Yeah.
Because the deflection is going high, maybe in the moist one, you can, now it's 5 millimeter, right?
Yeah.
You may increase it to 7.
Okay. It's going to be hard to remember all this. I think there's
I
a
think,
data logging
if we do
thing.
everything 10,
Yeah.
I think
for
10 is fine.
blending, we do everything 10. For
You do it
this
at
groups,
10.
yeah.
From next onwards, do everything at 10. Because it's taking too much time.
You want to leave the buckling and then we see if we have time to do it? Or
They
you
have
want to
time.
run it on
Do,
a
do,
rig-
do,
video?
do you have anything else to do after this?
We
Immediately?
have the two I-beams. We're doing the wet one,
Okay.
dry I-beam and wet I-beam. Do you want to run the wet I-beam?
No.
We just run this one as wet and then one dry I-beam and that's it. So you have a,
Yep.
you show them that
And
wet.
we can put a full video. Tomorrow, probably we can do the whole thing and give it to them as a video, right?
So you want to use the videos from tomorrow instead?
Yeah. Tomorrow will be better probably, okay?
They have a class after, so
Tomorrow.
no.
But tomorrow we have got only one batch
Okay.
and
Yeah, only
1 hour 20 minutes.
What time is it?
Tomorrow it starts at 1 o'clock. So tomorrow we can do the full and we can tell other students watch it live.
We should have put the sheet on.
So what we plan to do, our next one will be moist, same beam with moist. So we soaked into the water. So you'll see how the moisture affects its strength and stiffness and the failure pattern. You got it, right? You got the explosion. Okay. Now what we are going to do, that we have got a moist one, we will do that, but then we have an I-beam also. But I think our loading rate was a little slower. Okay. So what we will do, you don't have to do the I-beam now, but tomorrow in the class, tomorrow we will do all of them and it will be live streaming. Okay. So you can watch it without coming here. Only third batch will do that. Okay. Or you want to leave them now? And because it will be too late, we can ask them to leave now and they can watch the live thing tomorrow, right?
It's up to you.
Okay, do that.
When will the lab report requirements be posted?
After the class tomorrow, so they have to extract the data. Okay. After extracting the data, probably it will be up on Friday.
Just like what we're supposed to do for the lab report?
Yeah.
And then it'll be due.
22nd. Okay. So what you can do, you can leave now. There are 2-3 more tests will be done, but that will be done tomorrow again also, and we will send you the link. You can watch it live. Okay. That's fine. Okay. Thank you very much.
I think we still have my midterm.
Yeah, it has corrected. Number should be corrected now. I think you got 1 or 2 marks extra.
Okay, so tomorrow I'll be collecting it.
Yeah.
Okay, thank you.
Or maybe Friday. Okay.
Friday.
Tomorrow, depending
During
on
the
how
lecture, right?
lecture.
Guest lecture.
Yeah, guest lecture. Okay. Now you start from the steel again.
Okay.
Or you can do the timber first. No problem. Okay. That will be good. You start with the timber. But this is a moist timber, right?
Yeah.
Okay.
That's okay. We'll go this one and go to dry.
Yeah. Then the steel.
And then
The second batch, please come in. Sorry for keep you waiting in the cold. Inside is cold too. The second batch, please move in.
Okay. See you later.
If you are in the second batch, please move in. Anyone in the second batch here? No. Please move in. So what we are going to do, please come in, move in, spread it around. You all have a safety glass, okay? Now what we are going to do today here, we will be testing some steel beams. Someone will have a rectangular cross section, some will have a hollow cross section, same area. We will have a column, a short column and long column. They are both hollow steel sections. So we will show you that how buckling can be converted to compression yielding. And we will have timber, roughly around square cross section. Then we will have timber, the same timber, one is dry, another is moist. So because moisture plays a big role. Then we will have an I-beam made of timber, okay. So we will do all the test, okay. Last batch could not see all of them. So tomorrow you will have another chance. We will live stream all the tests because for the third batch. So you can watch it again, okay. And after tomorrow's test, they will extract the data. I will take one set of data, and that data we will send it to you in as an assignment with some questions. So you will analyze them, and I am giving you enough time, as we all agreed. You will have December 22nd, right? So this one has already started. So we are doing the test from your practical point of view. I discussed it. Should we do that in load control or deflection control? Deflection control. Anybody votes for load control? No? No. So it is in deflection control. Why is it so?
So that you can see the load that's developed.
Yeah, because it is, then what happens, you can see the full load deflection curve and yielding and everything, and moreover, the failure will not be explosive, okay. If you miss to press the button, it will just bang, because it is looking for the higher load. But in this case, you are looking for higher deflection, particularly for the steel and all these things. The yielding can keep on, it can carry on the same load, going through the deflection. So that makes it safe to test, okay. So we are moist timber cross section, right? So it's in deflection control. I think we are putting 10 millimeter per minute, 10 millimeter per minute. So you can see the deflection curve. Those who cannot, it should be there, okay. You can see that this is incidentally that starts from in a reverse way. It goes like that. So initial you may say a little bit of nonlinearity. That is because it is settling in the right place for the testing, okay. From your common sense, is a moist wood and dry wood, which one do you think will be more brittle? Dry one, right? And which one will have higher stiffness? Dry.
Yeah.
Yeah, it has already failed, right? So this is the only one which you, in the timber you get some explosion, still you don't get it, right?
Yeah.
So you can quickly put the dry one now. And remember
Yeah.
the load. Remember the load, how much load it carried. It's gone.
It's gone now. Yeah, I would like to check on the other. So you want to get another dry one? Oh, it's already there? You already put it? That was a wet, yeah. So we'll go.
Because it depends on the fiber orientation. When the knots are there, it will depend on that. But hopefully the dry one will be higher. Okay?
Yeah.
Because you already just got a knot. Can you do that? We'll see it under the impact. But as to what you get, your design, that is based on hundreds of steps. So this is a the same one, but it is not soaked into the water. Got it. Okay. And are you going to create a new link for the live streaming tomorrow?
Yeah.
Okay.
Yeah, of course.
So send it to me tonight or tomorrow morning.
Yeah.
So I'll send it to them that tomorrow we'll run the full range because now we are well prepared.
Yeah, yeah. So we're still doing everything right now.
Today,
right?
yeah.
Good.
But tomorrow we'll do from the beginning still and all this thing. And I'll be here tomorrow.
Okay.
We started.
Honestly, I didn't even find it. I was like,
Yeah, we're on a 5 now.
Let's do timber 5, steel 10.
Okay.
Well, the wet one was at 10.
What one?
We knew it was gonna go.
Yeah, way
But
more. So.
tomorrow you maintain one. Okay, so all timber of the same rate. Maybe timber you do it at 5, steel as 8.
8? But the first bar takes a long time. 8. I think if we go 10, we'll make
10.
it a little bit.
It's 200.
Yeah.
30 million anyway. So, a couple more minutes.
It's 330. I think it will go to probably 500.
Yeah, I think the previous one was close to 500.
Is it?
Yeah,
It could
somewhere
go higher
around.
than that. This is
I mean,
dry one.
the previous dry one. I meant,
Yes,
yeah.
oh, then it should go to 500. 450. It's good. It's going down. Oh, it's there.
No, I think it was just
Micro breaks.
yeah.
Not doing it.
About 600. Yeah.
Well, it almost never fails. Here, when you do your calculation, it's a moment.
There's no way that it's that straight.
I'm just gonna invest.
It looks very flat in the stream.
Yeah, it does. Yeah. Is it?
Yeah.
Is this wrong? Because surely there's some force in there.
Well, yeah. So that's a 1 kilonewton.
Oh, okay. Oh, it's just not as high as. Okay.
Yeah. And that's the maximum.
That's fine. 25 millimeters.
I think maybe just the perspective with the fisheye makes it look more straight than what it is.
Yeah, it's like,
Yeah.
because then you look at that.
Yeah, you're
Yeah.
looking back at it. Yeah.
Thank you. That. Yeah, I think that shows the curvature a bit more now. Yeah. Surprised how much he's holding, yeah? I will just break all at once. All that that area underneath that's the energy, right? So the force by the displacement throughout. So if you do an integral under that surface, So that will go all at once.
The integral under the surface is the
Yeah.
ductility.
There would be, yeah, there would be the energy that is absorbing through the process, because that's the force you're pushing through how much is deflecting, right?
Right.
So that would be the energy, the total area, right?
And
And
the
then it will
slope is the
release it all
force.
at once. It will snap, right? So all that energy will be released at once.
So does it fail in flexure then, or does it fail in shear?
Good question. I think it would be probably in shear, but that's something you might want to ask Falcone just to make sure I don't want to be saying something stupid, which is getting recorded too. Get to look at the diagram again. I can't remember how that looks like for this, which is pretty simple actually.
It's amazing how much it deflects.
Yeah, wow, that's how they made the bows. Yeah. So I was telling them how if you look at the curve there, like you have the deflection and the force over time. So the area under that is going to be the energy that is absorbing, right? So one that is going to snap, all that energy will be released all at once.
Dodgeball on Thursday.
Because now it's getting accumulated in the deflection. See, if there was a bow, that would be the energy will go into the arrow, right? So.
He's getting surgery on Thursday, so I don't know if he'll be like
I'm very
recovered from the
impressed that
anesthesia.
it hasn't broken yet.
Yeah, that previous dry sample didn't go that far. I think maybe half of this. Yeah, so, but again, it depends inside if had and not or something, right? So.
The concrete ones, you just like don't see the deflection.
No, yeah, wow. Yeah. Yeah. There you go. Yeah. Yeah.
It's a cool break.
Guys, you can see
Yeah.
here the load carrying capacity is higher, and in the timber it's very difficult to predict exactly how it will fail. You can, because fiber orientations in two beams will never be the same. Okay, so that's one thing. So I'm leaving you in the good hand of Armando.
Yeah.
But tomorrow we will record the whole thing. So you can watch this live.
This is how the previous one broke, by the way. This is dry, yeah. Previous sample, yeah. Are we doing the I-beams at all? Are we doing the I-beams?
I thought he wanted to go backwards.
Yeah, it's just that if I record all the way to the I-beam, then I don't have to, I'm not going to record the rest.
Then do
Yeah.
the dry.
Yeah. Well, we'll do the I-beams first because, when I do the recording, I mean, we have one extra that we did, but so I don't duplicate everything. Yeah. So okay, obviously that's the wet and that's the dry. Yeah, clearly. All right. So we'll try I-beams now, and we'll try. What do we want to try? The wet or the dry first? Dry. All right. Here it is. Yeah, it's pretty good. Yeah. Okay. Yeah, I would just go all the same. So that would be. All right. Yeah.
How would they produce this? Would they glue the flanges on, or would they cut this?
So that was making it. So it was just. I think it just cut through. Yeah. See, it's a single piece. So it just removed the extra material. Yeah.
That would be a lot of waste, though, if they didn't do it smartly.
Oh, well, I mean, this is how this was done. Right? Just so it was. But obviously, if you have a wooden I-beam, you wouldn't make it this way.
Okay.
Yeah. It would be.
You use like
As you
glue
said.
and
Yeah. Just yeah.
I noticed for the concrete one, there was like the rubber pieces underneath the blades.
Yeah, but you don't have to worry about this here because it's a ductile. Like if you think about the wood, it will adapt to the shape, right? The concrete you have, it's, as you see, there is no deflection in concrete. Basically, it takes the load and then breaks. So if you have any, like stress points where it's pushing on, it can affect the results. So the pads kind of account for distributing the load more uniformly.
Dock blocks actually have wood. Like they're trying to make more reusable ones because they used to be like fully made out of wood.
Yeah. So the test is running and it's already at 3.5 kilonewtons. And it's gonna go pretty soon probably. Yeah. Sorry, it's gonna move out of the way.
I guess it's bearing on like a infinitesimally small point.
Yeah. So is this the same cross-sectional area of the
Pretty close.
Yeah.
Yeah.
So the cross-sectional area is pretty close to this, but you can see this is holding up a lot more. It's 3.5 kilonewtons versus about 1, was it?
Oh, you see it's
Yeah. Yeah.
Which
Yeah.
torsional failure? Lateral torsional failure?
There we go. I think we are good here. Yeah, okay.
It's not true failure.
Yeah, just smash it. So before we do anything, do you mind to stop that and restart it because I had to switch battery? Just stop. No, just stop the recording button, the red button, okay? And now we'll start again. Ready? 1, 2, and 3. Okay, go. Good. Okay. All right.
So do these all have the same area, Armando?
Approximately, those two have about the same area. So you can compare how the different will behave. Yeah, that would be the same. The difference it is wet. So this one was wet. Yeah, just. No idea. I'd have to ask maybe Bastian knows something, but I doubt. Excellent connection. Look at that. Yeah. Okay.
houses
city, you're
were-
pretty. Yeah, as long as it's good. I like to be close enough to my family and everything that I know. I mean, it's kind of BC or Alberta in my mind. I don't really want to move to Ontario.
So what do you expect is happening again with the wet one? Just some idea of the square cross section, right? So you'd expect it will act more ductile, but also the overall load capacity should be reduced. Matter of fact, it's already kind of we're at 2 kilonewtons already, and I say it's pretty much done. Yeah. You see the load is already going back down. The plot is inverted, obviously, right? So. Sure. I guess we can stop it. Yeah. Sorry? Yeah. Okay. All right, so the load is already going down. We don't go any further because it's getting all twisted up. We don't want it to go shooting somewhere. I guess we go to steel now, right?
Sure.
Yeah, we're done with the wood, right? Yeah, square, yeah. Thank you. Great. Same feed rate, right? 10 mil. Yeah. You see, it almost looked like it didn't fail, right? Yeah, clearly it shows a little bit of something happening there. But. So, steel cross section, and that's the same cross section area of this bar I take, approximately, right?
The same, yeah.
Yeah.
It's the same,
Yeah.
and then this is a 1x1
Yeah.
compared to the wood, right?
Yeah, yeah. Okay, so we switch into steel now, and we'll test the square tubing, and that's the same cross-sectional area of this bar. So we'll test them more. You'll see that obviously, because of the moment of inertia, is much larger than what you have here, will withstand a much higher load capacity, right? So the feed rate will be the same. We'll go at 10 millimeters a minute. This will deflect a lot, so it will take quite a bit longer, yeah. Yeah.
Yeah, what's that? I mean, that is oh, that'll be good. No, I'm thinking summer this year is my last one.
We can go further with this one.
Yeah. Well, it's done now. Yeah.
Finally onto the technical line. You know, it's kind of stressful. It's been so easy to pick classes.
Term's almost up, huh?
Oh, it's crazy fast.
Yeah, I know.
It's so slow at the beginning, and then it just accelerated right through to the very back end.
So, 2 kilonewtons? 2. Yeah, we are ready at 2.5 kilonewtons.
Yeah.
12 millimeters displacement.
You know, it's funny, I'm in CIV 200 class.
Yeah, yeah.
We're doing the final project, and like the amount of stuff I've learned from my past classes that I'm trying to integrate,
Yeah.
it's like completely overkill in some sections.
Okay.
And they're like, you're doing too much. I'm like, yeah.
Nice.
It's weird how the prereqs work. You don't need a lot of second year classes to like go on because I had 2 fall co-op, right?
Okay, yeah, I see, yeah.
But yeah, I'm graduating on dynamics.
Oh, really?
Yeah, because you don't it's not prereq for anything. I would think for like earthquakes or something, but no, nothing moves, right? Don't want it to move.
Yeah. That's right.
How long will it take for the bridge to fall down?
3.5 kilonewtons. How far did we go before on this?
All the way down to the bracket,
Okay.
pretty much.
Yeah, so we're back. Which is also why it's
Yeah. Yeah.
I hate to be mean. Do you have like a chair or anything that I could
Oh, yeah, of course. Absolutely. All right. There we go. Yeah, sure. Yeah. We're pretty close to getting to the bracket. Well, you can see here too.
I think you were interested in like these, not necessarily favorable.
It's yeah, it's pretty flat to be honest.
I'm gonna touch it so we can
Yeah,
start
yeah.
going.
Yeah. Still going up a little bit. 4,000 newtons. So this was 10 millimeters a minute. Okay.
He's got to allow for 10
Yeah.
minutes per test.
Yeah, it's starting dropping now, as you can see. So they started dropping now. You see?
It's kind of hovering around 4.
Sorry?
It's sort of hovering around 4 kilonewtons.
Well, you started now. You see that it's curved.
now
Yeah,
it is.
no, yeah. Yeah. So yeah, so we are done at say 4,000 newtons. We'll do the flat bar, I guess, right?
Is that a new one?
Yeah.
That might be the old one. We already tested that.
Okay, we are getting, yep, here's the new one. There we go. So do you think there was a plastic deformation on this one? Here. Okay. You're strong. You bent it that much by hand? Wow. Yeah. Yeah. Here. Yeah, I'll give you a good one here. Hold on. Ah. Come on. Strong. Yeah, look at that. Yeah. Yeah. It's, just to be consistent throughout. It's going to still be like 5 minutes, right?
You don't even see through it anymore.
No line of sight, eh? Yeah, there you go. Okay. So new test is started. So what you guess is going to be the maximum load on this? Yeah, we take guesses.
Maybe like 2.
2 what? 2? 500. Any more guesses? 1. Okay. You're all right. Yeah. 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 Yeah.
100 kilonewtons.
Yeah, actually right now it's at close to nothing. It's still within the error margin of the machine, yeah. About 20 newtons right now. 30 newtons for now. $50 newtons is already 15 millimeters deflection already.
Jeez.
Yeah. Yeah. The same bar, if it was turned 90 degrees, it will give you far more resistance.
Right, yeah.
Yeah, so, because the moment of inertia are completely different. Like, I have some calculation. Do you remember how to calculate the moment of inertia? You will have the product between the two, but one of the two will be to the cube, right? So if you invert it, means what you have to the cube is the other side, which is probably, what's the flat bar? It's a 1 inch, so it's 4 times as much. So that would be what, 12 times as strong, right? Like the moment of inertia would be 12 times as big, right? So massive difference. More than 10 times as strong. That wasn't us. So you got 170 newtons. Yeah.
I was really off.
Yeah. That's okay. That's okay. It's good to make guesses, so then you get appreciation of what it is, right? Yeah. Yeah, 2. So somebody was close with about 500.
That would be insane.
After this one is a backling. This is the last one in bending, right? So this, after we are done with this, we'll do some buckling, okay? So we'll have columns, and we'll compress them, and we'll see when they buckle, okay? Have you done calculations on the backlink in class. Okay. Yeah. Okay. So some of the aspects are about what are the boundary conditions at the ends, right? If they're pin or if they're held. So the ones we are going to be testing here are going to be pin, right? So we'll screw them on the top and on the bottom. We have a bolt going through, okay? And I have posted here, you can come by after and add the calculations of what the estimate is. I have the cross section, so the moment of inertia, the length, and the estimate using the Euler equation for me was 10.5 kilonewtons for the critical load. And the previous experiment, the critical load was almost 11, so it was very close to that estimate. Yeah, so, yeah. 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 We'll go just a little bit more and then we'll stop this, okay?
Just until 500.
Yeah, we'll stop at 500 just to make somebody happy, yeah. Yeah. By the way, anybody familiar with MatCAD? So what I use here is a MatCAD. It's a clever application. You can get a trial version, but then I believe if it expires, you can still use it with basic functionalities. You can write down equations and you can write sentences, so it looks like a Word document. But the equations are active, and as you change a number, everything changes to go with it. And you can overwrite the units. You can even sum meters with inches. It will automatically do the conversion the way you want. And if you have inconsistencies in your units, it will give you there is an error. So this kind of checks for you what you're doing. So I'm just basically giving you ideas. Oh yeah, 540. Yeah, we're going to stop it here. So I'm giving you some good ideas about how to cheat in your assignments. When I was an undergrad, especially I had some like hidden mass transfer, really complex equations, and many problems were very similar. So I'll copy and paste and just change the values. And yeah, it didn't help with the midterms. Sorry, Prof, can I use MatCap for the midterm? Yeah, that's it. Yeah, okay. Okay. So I guess we'll prepare for the backlink after. So for backlink, we will do that length, that sample I showed you, which is 34.5 inches or about 870 millimeters. And then we'll have another one that will be much stubbier, much shorter. That one we will not actually take to buckle. Will be much higher load, and I'll explain after why we don't want to go that high. So we'll only buckle the longer sample. Okay. Do you want to use the faster, because we like to go way up, right? With the backlink. Yeah.
I'm going to leave this one at first, so I have safety.
Okay. All right. There you go. You got that.
actually larger ones.
Here we have.
Building envelope and architect side of things.
So these two tests will run a lot faster because obviously you're not going to have much deflection before that's going to start buckling. Okay? We will actually run it slower. What we decided to run the buckling at? Yep. Everything okay?
I don't know how to do this.
Oh, it's not going down? Well, take it to that. Move it to, yeah.
I
That-
think if you went up,
Oh, oh, that's,
I can run it from here, but I have to.
no, it's, yeah. That's odd. So if you're moving it with this, it doesn't,
No, it goes up because he wants to park it higher.
okay, no. Well, and what if you just push it now? It doesn't just by hand, just holding the arrow. A stand, and this is
This is retract.
retract. Okay, try to retract it. So it's. Yeah, and I think that, yeah, it's, I believe that's going down, right? Yeah, it could change the settings, which. Can change the settings at which is going down, but yeah, anyway.
I will have to ask Solomon.
Yeah, I believe it's. I remember he showed me how you change the settings for when you're just moving it.
He might be with the other software.
Yeah, but
You can also do this, but I don't.
I'm just I don't want to try it right now, but.
I'm gonna head back to the office.
Yeah, okay,
Thanks
sounds
for
good.
letting
Yeah,
me know.
yeah, for sure. Yeah.
So just every time we press this, I don't have time to lower it down.
Yeah.
So maybe we allow like a couple more minutes per test just to lower it.
Yeah.
This was just one thing.
Yeah.
16 mil. Yeah. You can start putting the bar on it.
Yeah.
It might be a little. Move it from the other side. It's a little way.
Was it? From the other side?
Yeah, yeah.
Okay. Yeah, it seems a little tight.
Yeah, that's good.
Oh, let's see what's going on.
I guess they're slightly different.
Yeah. Oh, come on. Oh, really?
Are you okay?
Yeah, just. I thought the clearance was a little bit. I think if I put it this way, I guess I have to go higher up on the other side. Slow in retracting, yeah. I think you're probably pretty good for the bottom. Yeah. Got a bit of a burr here. Okay. All right. All right. Okay. Oh.
It's not in line. I can. You got it there?
Yeah, I can't see where the hole is. Oh, it's a little lower. So, yeah, a little bit lower down. A little bit lower down. There you go. Yeah.
You feel like it's.
No, it's pretty loose on this side. But, you want to lower it down a tiny bit? Oh, you go, maybe. Yeah. Yeah.
Yeah.
Yeah, maybe just. Can we persuade him? So the little blocks here.
You see I
Yeah,
shaved-
shim the one that goes on the inside. Yeah.
Does it fit? I can extend it a bit. If you,
Yeah, maybe.
Now it should.
Oh yeah, no, no problem. Yeah. Okay, it's good. So. Okay. Okay. So we are just about ready to test. So you may notice that between the round plate and the rectangular plate, I put two shims on the two ends, because this is allowed to basculate that way on the bending setup. Because if you have it rigid, what's going to happen is that you may not have the same load on both rollers, right? So if it's allowed to do this movement, then you know that you have a pivot point and the load will be equally distributed. In this setup, we want it to be rigid. So we put two little shims so that it's not allowed to basculate anymore. Yeah? What did we do earlier? Was it one? I think that was pretty good, I think, for one, right? 1 millimeter a minute? Yeah, okay, let's run it the same. So when it's in compression, right? What do you expect to be the response? Like obviously in bending it will go a little bit, bowing then eventually will reduce. Here you're compressing like a bar. So what is the expectations to be if it's in the elastic region? Just like in tension and in compression, you're going to have a linear response, right? Because it's elastic, right? It's like a spring, okay? But when we're going to be testing, and you'll see the plot, they will be pretty linear at the beginning, and then before buckles is going to be going non-linear. It's going to change the relationship. Why you think is that happening? Sorry?
Because the steel is yielding?
No, not really, because the buckling will happen at much lower force than what it is the heel strength. But so you're looking at the maximum force is 10 kilonewtons, and if you look at the stress in the bar, I calculated it inside. That's basically the cross-section area, and the force is 60 megapascal, 70 megapascal, and the heel strength of steel is 250. So you're well below that.
Was it when it reaches like a plastic? I'm just thinking of like that
Yeah.
graph.
Yeah.
When it reaches like a plastic.
Yeah, obviously something is going on, but the question is where. Okay. In the calculations, I have one analysis here that you haven't done in this course, but is bearing stress analysis. So if you're compressing hard a bar like this, where do you think, if it's not buckling, where is the highest stress points in this bar?
In the middle.
In the middle, okay. Any other ideas? Think about how that is set up, how it's supported. Yeah, it's where it's held, right? If you look at, it's a thin wall. You have a bolt going through. So these little thin wall sections are going to bearing all that weight. So where the steel is getting pushed in the holes here, where it's going to see the most stress, okay? And that's what is called bearing stress. Okay, it's buckling already, is it? Is it buckling already? So it did buckle at what? At 9, I think, right? I think this buckled at 9 kilonewtons, so a little bit lower. You see how it's curved, right? So when I ran the analysis for this, and when we designed the beams to do this test, the one thing that was of my worry is what would happen here. And that calculation says that if you're at 10,000 Newton, in the where it's carrying the load on the holes, you have 400 megapascal, and the heel strength of steel is 250. So it's obviously doing something here. It's literally pressing and deforming at the holes. That's why you have that non-linear response at some point. It's the holes are deformating. Yeah. So it's not the bar itself, the holes are getting deformed. And that's why in this other test that we'll be doing, we will only push it to maybe 15, maybe 13 kilonewtons, because you'll see on that one, you will get this, because this is going to be super rigid, it's short and stubby, it'll be very linear, and then all of a sudden it start going like this, and that's, the holes will look ovalized after, okay? So we done this test, you're just bringing it up, okay? So now there is zero load, right? No, there's still some, okay. So we'll be left with a little bit of deflection in it. Yeah. It will go almost entirely straight at the end, yeah. Huh? That one bolt came off from the top, eh? So we'll have to thread that back in before. I suspect that those shims may be carrying quite a bit of the load, and then that made the thread come off. So you need to come down a bit so that gets a little bit more flat. There you go, okay. Before this is supporting, before you take it out, you see that big bolt? That needs to go back in. Yeah. So I would try to do that in before anything else. Can you reach that? To come down a bit. Do you want to take it out and then we lower it? Okay. Needs to come down anyways. I hope I didn't damage the threads.
Yeah, that's what I was worried about. When I shipped it, I was worried about this happening. I might be able to thread it.
Doing it.
This one was already hard to do, just thread it.
Yeah. Is it?
I think that's it. Do we want to just not shim it this time?
Okay, sure. We'll leave it.
And just fasten the bolt
Yeah.
all the way.
Because it doesn't have a lot of engagement in the thread, right? So. Okay. Okay. Can't see from this side. Yep. Yeah, a little bit lower, yeah. And higher now. We need to go a little higher. There we go. Perfect. Okay, so the previous sample, which is, where did I put it? Here. So this was 34.5 inches long, and that one I believe is 18. I'll double check. So it's still got a little bit of an arc. Yeah, here.
Are these considered pin supports because
Yeah.
they can rotate?
Yeah, exactly. There's a pin.
But when we're doing the horizontal beams, does it matter what kind of type of support they are, or is it just a clear span?
Well, it's supposed to be able to roll so that there is no moment. You don't want to have any moment applied at the supports for this specific setup. So it's supposed to basically roll around it. Yeah, yeah.
Very brittle. That's the most difficult part.
Yeah, that's what she said. There we go. There is a little bit of twist in there, yeah. Yeah, perfect. All right. Almost done. Last test. Okay. Okay. Okay, this is a simple demonstration again. So we'll show that if we go somewhat higher than where the other one buckled, it will still withstand no problem. And if you see a nonlinear relationship, is due to the at some point to the deformation of the holes where it's supported at. Right? So test is running already, right? So we're already at 7 kilonewtons. You see how at the beginning it's linear, and then it starts kind of changing. Based on this equation here, it was already showing approximately at 5 kilonewtons. So you start seeing already in a plastic deformation approximately. At 10, you have 400 megapascal, so you say 5 would be 200, and the heel strength is 250. So maybe 6 kilonewtons, and you start seeing that deforming somehow. The initial deformation is not linear too, because just is kind of adjusting itself in the holes and whatnot. Yeah, it's somewhere around there. Did you stop it already? I'd say yes. I think we should stop it. Did you stop it already? Okay, let it run it a little bit longer. Just to see what's happening at the holes, okay? All right, maybe I'll stop it now, yeah. So 16, so substantially more, not buckling whatsoever, yeah. But we'll see what happened at the holes, okay? All right, so that's loose now. No, not yet.
No, it takes a while.
Yeah, okay. Let's It's going up. What's going on? It's going, so push it down, like, okay. Yeah, 17 kilonewtons, so. Yeah, try to retract, see what.
How many more
Oh,
tests?
yeah. No, we're done. This is the last test. We're finished.
Actually, unlock it and just move it until I can move it. So I don't know why it doesn't.
At the hole. Yeah. That's why like it would yield at the hole. Yeah. That's what slice through.
Okay. Yeah.
This displacement, so it's not gonna just like slice.
Okay. There you go. Okay, it looks it's loose now. Okay. Okay, you want to bring that up? You can see how the whole. So the machine, when it was estimating the deflections, it's the machine that is moving, right? So it's not measuring what's happening inside this bar, but what's happening at the hole's position. So that deflection is part of what you're measuring. So, okay, here, there you go. And I guess that concludes the demonstration. You're welcome. But now that you're nice and cold, you go and take a hot shower, right?
Yes.
Okay. Okay. Oh, yeah, you're welcome. Thank you. Bye. So I literally need to run